Hi guys, in this video we are going to learn how an OPAMP can work as an integrator. In our previous video we have learned some basic applications of an OPAMP. If you haven't watched those videos, please watch those videos first. I have given the link in the description as well. So without wasting our time, let's move on to integrator. And also, if you are new to this expert tutor channel, don't forget to subscribe it. Let's start from the beginning. So here also we are going to have one resistor. With that we are going to have a capacitor. The reason why we are having this capacitor with this op-amp and resistor is we actually knew that the relationship between the voltage across the capacitor and the current between the capacitor is going to have some differentiation relationship or else integration equation. That's why we are going to use this capacitor to change our input to from one function to that integrator function of the input function. So, and also we have provided a negative feedback, so I'm going to mark it like this. So these are the terminals you need to remember. The reason why we are giving a negative feedback, which means we have connected the output to the input terminal, the negative terminal, so that we can tell the voltage from this positive terminal and the negative terminals would be equivalent. So let's start from these steps. Actually, we are going to repeat the same step which we are doing from several videos. So let's start from this one. Here we are provided Vi, and you can directly tell the voltage from this side is going to be 0. The reason is we have connected this 0, the plus positive terminal, to the ground. If you connect it like this, we can directly tell since there is a negative feedback, it's going to be like this. This negative terminal is going to have 0 voltage. And also if you mark the current, it's going to be going through this resistor. Let's mark like this. If the current goes through that resistor, definitely you can directly tell that current won't flow through the input of an op-amp. So that if there is an I over here, it should move through this capacitor. If there is an I, it should move across this capacitor. Otherwise, it won't be possible. So that's why we are going to mark the I like this. So now we have completed this diagram. Now we can directly write the equations. If you use the Ohm's law for this resistor, you can write that Vi, the voltage difference is going to be Vi minus 0 is equals to I into R. So now let's move on to the capacitor and write the equation. For the capacitor, we have learned that Q is equals to CV. The Q is the charge across the capacitor, and the C is the capacitance of the capacitor, and the V is voltage across the capacitor. So if you differentiate these Q and these equations with T, the reason is here we don't need this charge. Instead of that, we are going to change this charge like this, dq by dt. We are going to differentiate that. If, as we all know, dq by dt is going to be equals to it, which means it's going to be the current across this capacitor. So let's mark it like this. We are integrating this. So we can directly tell it's going to be the current of across the capacitor, and C is a constant you can take out, and it's going to be dVc by dt. So this is the thing. So we have marked all the stuffs. The next thing is where the VCs, where we need to mark the VC. You need to be very careful when you are marking the voltage across the capacitor. According to this image diagram, I have marked that I is going to go from this side to this side, from left to right, which means if the current is flowing from left to right, you can directly tell the voltage is higher in this peak. We are assuming that voltage is higher in this peak. So what you can do is we are going to mark the VC in this direction from right to left, because we normally mark the voltage in the increasing side of that voltage. So we knew that since we have marked the current is flowing from left to right, the voltage across this capacitor is going to increase, which means the highest voltage would be in the left side of that capacitor according to the I we have drawn. And we actually know that this point voltage is going to be V output. So what's the relationship within VC and V out? So let's mark it that first. Before that, what I'm going to do is let's integrate these both sides so that we can directly substitute the value for VC. So the thing is, we have marked like this. Here in this side, VC is increasing, which means if you take it as 0, here the voltage would be VC. But in the real context, here this voltage is we have given as a positive voltage V naught, and this is going to be 0. So how to mark this one? What's the relationship is going to be between VC and V naught? It's going to be minus V naught. The reason is very simple. Here we have marked like this because of the I we have denoted it's going to move from left to right. We have connected from left that VC is increasing towards left side. From that, we can directly tell if you consider this right side as 0 voltage, it's going to be VC. But in the actual scenario, we are going to have this V naught and V output, and this is going to be 0 since we have connected to the ground of this positive terminal. So you can directly tell VC is going to be minus V naught. So here we can directly substitute minus V naught over here, or else since to find out what's the value of V naught, what we can do is we can directly integrate IR. We can directly integrate these two. So let's begin with the substitution of I to this equation. If you substitute that, we are going to get VI divided by R is equal to C dVC by dt. We need to change it for minus V naught. So let's change it as soon as possible. And also, here we need to find the V naught. The output should be the integration function of Vi. So we need to show in this format. When we are providing input, it should integrate that input and should show as an output. So what we can do is you need to integrate both sides so that you can directly get rid of this D and you can get an integration function for Vi. So let's do it at first. So dVC by dt is going to be equals to Vi divided by RC. So if you integrate it in both sides, you are going to get VC is equals to integration of Vi. Anyhow, the 1 over RC is constant, so you can put it like there. And VC, actually we have proved that VC is going to be equals to minus V naught. So you can write it like this. And if you put this V naught, you are going to get minus 1 over RC integration of Vi. So this is the thing. This is the equation. This is a circuit. And if you make a circuit like this, you are going to get an integration of input signal you are providing. But there are some constants. So if you adjust this to 1, you will getting the integration. But always remember there is going to be a phase shift of pi difference. You will have, theoretically it's going to be pi, in practical it might differ a little bit. So here we are going to have a phase difference of pi. So I hope this video would be clear for you. The main aim of this video to prove this equation, and also you can also change this diagram little bit and get a differentiator, OPAMP as a differentiator. What you should do is you need to connect this capacitor in this position, and you need to shift this resistor to this position. And please try it, and you can derive an equation. You can, in the exams you need to actually memorize this equation, otherwise it's difficult. Minus RC, so sorry, this is differentiation. So we are going to get dVi by dt. You will be getting an equation like this. So if you interchange C and R, and if you try that, the same steps, you are going to get the V output as the differentiation of input you have provided. So This is a basic thing. So if you want an example, I can also explain that as well here. So let's say if someone is providing a DC voltage here as an input signal, you are providing a DC voltage. So let's mark like this. So this is the input with respect to time. You are giving an input voltage, which is a constant voltage. So let's say you are giving a 5 voltage. So you need to find out what's the output you are going to get. So this might be a question for you in the exam. So what you can do is, if you memorize this equation, definitely you are going to get an output. If you are giving to an integrated circuit like this, minus 1 over RC. So they will be providing this RC, and it's going to be VI dt. So here we actually knew that VI is going to be phi, a constant, into dt. So if you integrate that, you are going to get 5, as well as, since there are no other thing, if you are going to get phi t. So this is the shape you are going to get. And also minus 5 c, these are the things are constant, and this is going to be a t graph. And always remember there is a minus sign, so you need to, so I think I don't need to repeat these things. This is going to be m into t, where m is less than 0. Always remember, sometimes you might be having doubt, if you integrate there should be a constant, but the thing is, if the capacitor is initially with not charge, it's not having any charge in this capacitor, the constant would be 0. So that's the thing. So we are assuming like that, since there are no initial charge, we are going to get this one. If you assume there is already a charge before you are connecting this circuit, or before you are providing that input, definitely it's going to have something like phi t plus c. So it's nothing a very big issue. You can directly mark it like this. So the thing is, what you are going to get is, you are going to get an output signal like this. So here for this signal, we are going to provide a new name. It's going to call as ramp. So the meaning of ramp is, we are going to get to infinite. The voltage output should increase according, in practical manner. Sorry, in theoretical manner, it should increase up to infinite, since with time, with respect to time, the voltage, output voltage, is going to increase. But the thing over here is, it will cut down at a certain limit always. The reason is, we have already learned, anyhow in theoretical, the AVD, like the voltage gain, might be infinite. Actually, if we don't give a supply power much, it's going to stop at this supply power. Let's say we are providing a minus VC as a supply power in the negative direction. If you do like that, you are going to clamp that graph after this position, which means it won't be increasing after that. Even if you are giving a minus 5 as input, it will go up to a certain limit. It's going to increase up to certain limit, and after that it should be clamping. The reason is, it can't go further because we are not providing so let's mark the VCC here, because we have already provided VC for capacitor voltage. So it's a VCC, which means the supply power. If you are not sure what's mean by the supply power is, we have already learned in the previous video. Please check those videos as well. So we are going to give another source voltage over here. So it can actually get the maximum of this VCC or minus VCC. So you need to remember that. I hope this video would be clear for you. If you have any doubt, please comment it below. And here comes the question. So now you need to prove this equation and figure it out to build a, to get a signal like this, to get an output signal like this. What input signal you need to provide in a differentiator amplifier? If you need to get a graph like this, the output as this with respect to time, what input signal you need to provide for a differentiator operational amplifier? This is the question. Please try it out in your own and try to put that answer in the comment section. Thank you for watching.